Today's video is the first in our magnetic fields topic, and we're going to spend some time going through a little bit about fields that you might have done at GCSE. We're going to look at what flux is, which is a new idea for us, flux density and flux linkage, just so we were able to use those terms throughout this topic. And then we will look at what happens to charged particles when they enter a magnetic field. So let's talk about flux first. Like I said, this is a new idea for most people. And really all flux is the number of magnetic field lines that we get here. If you look, you can see that in here you've got a lot of flux lines and you're getting fewer flux lines out on this side here. So it's really just the number of lines. And the symbol that we use for flux is phi, and it is measured in a unit called Webers. Now again, we very rarely use flux just by itself. Instead, we use it to determine the magnetic field strength, or what's known as the flux density. So if you imagine a square, like I've drawn here, of 1 meter squared. Obviously this is not 1 meter squared, it represents 1 meter squared. We're going to take this area and we're going to move it into these sections of the magnetic field. And if you were to take just 2, for example, and I'm drawing them in here, not very well, but drawn in nonetheless, you can see that in 1 meter squared of area out here, we have 3 flux lines. And in 1 meter squared of area on the inside, 1, 2, 3, 4, 5, 6. There are 6 flux lines. So that means that the flux density is 3 Webers per meter squared on the outside, and 6 Webers per meter squared on the inside. Now the Webers per meter squared is given a name. It is called the Tesla, capital T. So that's the unit of magnetic flux density, and it's basically telling us the strength of the field. We've met this before. We know that stronger fields are represented by more closely packed lines. So we've been talking about this since GCSE and in electric fields when we drew electric field diagrams. But here we've got an actual unit that we're going to use for the flux, the field lines, and a unit that we're going to use for the flux density. We could use this diagram as another example of how you consider flux density. Here's our meter squared, and we can see that the picture on the left has a lower flux density than the picture on the right. Flux density is given its own symbol, so that is B, and we've said it is measured in Teslas. And because our flux density is the flux per meter squared, we know that B is equal to phi divided by A. And of course we can rearrange that to phi is equal to BA. And that is something that we're going to find particularly useful later on. The third term that we need to be familiar with is this idea of flux linkage. And this really only comes up later on when we talk about moving coils into magnetic fields, but we're going to explore it now. So let's suppose we have a coil of wire. Fairly simply drawn coil. If you move that coil of wire into the magnetic field, then what happens, of course, is that you get flux lines passing through that wire. If we now count the number of flux lines that are passing through that wire, we can see we've got 1, 2, 3, 4, 5. So we would say we have 5 lines of flux linked to that single coil. So its flux linkage would be 5. If we add a second turn on this coil, and I'm going to add this in black so it becomes more visible. So we've added another loop. Adding another loop multiplies the flux linkage because the flux linkage is per coil. So if you've got 2 loops, then your flux linkage becomes 10 because we have 10 flux lines to 2 coils. And so the flux linkage is a function of both the lines of flux that are passing through your coil and the number of turns that you have on your coil. Now, flux linkage isn't given a symbol by itself. It's basically given the symbol that shows you how you find it. So flux linkage is simply n phi, where n represents the number of turns of the coil. And again, in another video, when I go through electromagnetic induction, we'll be coming back to this idea of flux linkage, and I will remind you of it then. Because it is a whole number multiplied by the flux, our flux linkage is also measured in Webers. The next thing we need to discuss is the magnetic field that you get around a straight wire, because we're going to start connecting permanent magnets with electromagnets. So let's remind ourselves about the magnetic field that you get around the straight wire. And we use what's called the right-hand grip rule for this. And you can see in this diagram on the left, it shows you the right-hand grip rule. If you point the thumb of your right hand in the direction of the current, then your fingers show you the direction that the magnetic field will have around the wire. And that's shown over in the picture on the right-hand side. We can see that you get a circular magnetic field produced along a straight wire like this. Note that the flux density becomes smaller as you move out. Again, if you moved your meter squared of wire or meter squared of area in here, the further out you go, the less flux you're going to get passing through that meter squared. So our magnetic flux density gets weaker as we move out. The other convention that I'd like you to notice here is how we represent magnetic fields. The interaction of electrical currents and wires and charged particles with magnetic fields is a 3D affair. And so often we have to talk about whether the field moves into the page, or screen in this case, or out of the page. And so we use the idea of an arrowhead to think about this. If an arrow is coming straight at you, all you see is the point. And so that's how we know that a dot drawn like this is representing the field coming out of the screen. And if the arrow is going away from you, what you would see is the fletches that look a sort of a star shape. So that allows you to remember that an X like this shows the field going into the page. Normally what we do with wires, rather than having them or using just a straight wire, is we put it into a coil like this. And there are a couple of reasons for this. First of all, the magnetic field of a straight wire is not very strong, and it decreases very quickly with distance, as we saw. So when you put it into a coil like this, it's called a solenoid. And if we look at these fields here, you can see that magnetic fields are vectors, and so the fields add up for each loop. And they're obviously going in opposite directions, as up at the top here, we can see it comes out of the page because we see the point. So the same thing can be applied to current as to field lines, and it goes into the page. I've drawn the purple X's in there to make it a little bit clearer. That means that the current is traveling in this direction through the coil, and the magnetic fields around each side of the coil will add up to give you something that looks a little bit like a bar magnet. So in each loop, you get the current running like that. This produces a magnetic field like a bar magnet. And in order to tell which end would be the North Pole and which end would be the South Pole, we can use a little trick. You have to imagine turning the coil so that you're looking right down at the first loop. And as you look at the first loop, you see the direction that the current is going in. So here we can see that the current is going down along and out along this wire. So it's going in a clockwise direction. And this little trick here, drawing your S with the two arrows on the end, because that means if it's going clockwise, it's a south pole, and conversely, on the other side, our current is coming in like this and around, and it's going anti-clockwise, and you draw a little N with the arrows on the end, and that allows you to remember that anti-clockwise currents down the end of a coil produce a north pole. If we now come back to our electromagnet, our solenoid, and what we need to do is imagine that we turn this and look at the ends. And so if you put your eye down here and you're looking at this end of the coil, you can see that you have a clockwise motion of the current through the coil. And if you look down here, it would be moving anti-clockwise. Again, if we use our little trick, clockwise means south pole and anti-clockwise means north pole. So this would be the north end of the magnet and this would be the south. borne out by the fact that the magnetic field lines are coming out from the north and into the south. Now let's talk about charged particles moving in magnetic fields. One thing you need to realize is that a magnetic field will affect not just magnetic materials, but also charged particles. And of course it affects wires with current through them, because current, as we know, is the rate of flow of charge, and so that charged particle that is moving inside the wire is affected in the same way by a magnetic field. So we're going to imagine we have a charge of minus q, so it's like one electron moving into this field here. And the important thing to remember is that as the electron comes in, that is its velocity. And its velocity is perpendicular to the field, and we can see here that the field is going into the page. And the velocity is perpendicular to that. That is very important. When you have velocity perpendicular to a field like this, you can use what's called Fleming's left-hand rule, which we also met at GCSE. Make sure you're using your left hand. And this is Fleming's left-hand rule. Your first finger is field. And so you point from the north to the south with your first finger. The second finger is the current. And this is conventional current. So that points from positive to negative. And that's a very important point we'll come back to in a second. And then your thumb points in the direction of the force. So if you can remember that your first finger is field and second finger is current, then naturally enough the third finger, the thumb, is going to tell you what the force is. If we then apply Fleming's left-hand rule to this situation, so your first finger is field, so that's going to be pointing directly into the screen. And that is where you start. It's always a good place to start. If you can, start with a magnetic field. Here's where you have to be careful about the direction of current. Now remember, this is a negatively charged particle and it is moving upwards, which means current, conventional current, is acting downwards. So you point your finger into the screen and your second finger at a right angle to the first one is going to point downwards. And then when you stick your thumb out at another right angle, it's going to be pointing in this direction. Now let's repeat this process for each movement, each position of this charge. Because of course, the force that pulls it towards the center is going to cause it to veer on its path a little bit. And if we do the same thing, Fleming's left-hand rule, for the second position, first finger pointing into the screen, second finger in the opposite direction to the velocity, you'll find you get a force in that direction, and in that direction, and in that direction. And you see that force is pulling you around in a circle. We will come back to the circle part of it in a moment. Let's think first of all about the factors that might affect the size of the force. So what is this force on this particle proportional to? Well, first of all, it's obviously going to be proportional to the magnetic flux density, the strength of your magnetic field. If you've got a stronger field, the charged particle is going to feel a greater force. The second thing that it's proportional to is the size of the charge. So a doubly charged particle will feel double the force of a singly charged particle. And thirdly, the speed at which the particle is moving. The faster it goes, the more force it feels. Which means our equation becomes force is equal to magnetic flux density times the charge on your particle times the V. Now remember, this applies when all three of our things are perpendicular: our field, our current, or the direction of the motion of the particle, and therefore the force. Now we said that this produced a circular motion on the charge whilst it was in the field, and the force is pointing towards the center. So we know that our circular motion equations are, this one in particular, mv squared over r, which means BQV is providing a centripetal force. So we can equate these two. BQV is equal to mv squared over r. That's going to cancel. If we do a little cross multiplication, we know that BQR is equal to mv. And lastly, r, the radius of the circle that the particle is traveling in is going to be mv over bq. This is a very important equation in terms of particles. mv, of course, is momentum, so you could write it as p over bq. But it tells us that the radius of a circle that a particle travels in is proportional to its speed, or its momentum, inversely proportional to the magnetic field strength and the charge. So when we do particle accelerators and detectors, this becomes a very important equation if you want to accelerate a particle in a particular radius around a circular accelerator, or when you're looking at the photographs you get of particles that come out after smashing them together. You can tell a lot about the particle based upon the direction and size of its radius. And think about the direction there for a second, because if this was a positively charged particle and you applied Fleming's left-hand rule, the force would be in the opposite direction. And so our curve would be like that. When I do my video on particle accelerators and detectors, be sure to check it out because I will go into this in more detail. One thing you have to be very careful of, and I can't emphasize this enough, what if the velocity of your charge is not entirely perpendicular to the field? Because there may be occasions when it's not. Now our specification says that actually our equation is bqv sine theta. So when theta is 90 degrees, sine theta becomes 1 and f is bqv. So that's the situation when our charge would be moving perfectly perpendicular to the field. That's the direction of its velocity. And so the theta is the angle that it makes with the field lines. But here's where you have to be careful. That sine theta very much depends on what angle that you're given in a question. So suppose we had this situation here where our charge is moving at this angle to the field. If you were given that angle there, there's a couple of ways you can go about it. You need to know what component of the field is perpendicular to the charge, or the velocity of the charge. And so you would then need the cos of that angle and not the sine. So you need to really think about resolving your components rather than just blindly using sine theta. If you're given this angle here, then you could find the component of the velocity that is perpendicular to the field, and in that situation, it would be sine theta. So you can either find the component of the field perpendicular to the velocity, or find the component of the velocity perpendicular to the field. Either one works. Just make sure you know exactly which theta and which vector you're using, and instead of just blindly following the bqv sine theta, pay attention to what the angle you're given and make sure that you draw your vector triangle so you know exactly which side of your triangle you are calculating. Now remember, of course, when you draw your triangle, the original size of the field is going to be the greatest length, so it's going to be the hypotenuse of any triangle that you draw. This gets quite involved, quite complicated, so make sure that you find some questions that you can practice doing non-perpendicular velocities and fields.